This is the walkthrough of the February progress test for Year 13 students. So I'm going to go through each question in turn. You can have a look at this alongside the paper if you have it, or you can have a go at the questions for yourself as you're going through. So let's start with number one. We've got an incomplete Born-Haber cycle for the formation of cesium iodide, and we've also got a lot of data. Now, we don't need the data table for part A, but you are asked to complete the diagram by writing the formulas, including state symbols, and that will always be the case on questions like this, of the appropriate species on each of the two blank lines. So if we take a look at the top line, we can see that from here to here, we've got CS gaseous becoming CS plus gaseous, and I gaseous going to I minus gaseous. So in a sense, we've got two options here. We've either got the first ionization energy of cesium, or we've got the first electron affinity of iodine. But we've also got to remember that electron affinity is exothermic, or certainly first electron affinity is exothermic. So that would be this one. And that means that the first arrow going up here of the two will be the first ionization enthalpy of cesium. That takes us to CS plus I, because that hasn't changed. And we remember to add the electron that has been lost. And obviously, you can do all of that hard work, but you miss out on the marks if you forget that crucial information. We need the state symbols as well. When we look down at the bottom, we can see that we are making 1 mole of solid ionic compound. And we can see going up here that we're going from the elements. We've clearly changed cesium, which is solid. But we're looking for the start of enthalpy of formation, which will always be this first one up on the left-hand side, going down to the ionic lattice. So we've got CS, but it's going to be solid because we're starting with elements in their standard temperature at standard conditions, or in their standard states at standard temperature, I should say. And we're starting with half I2, which is also solid. So we've got the marks for each of them. So let's go on now and have a look at the calculation. We want to calculate the standard enthalpy of atomization of iodine. Now, what I'm going to do here is I'm going to highlight what the two routes are around this cycle. There are many different ways that you can do these calculations. You can change directions of arrows and change signs. I tend to find this is the most straightforward method, and it can help you to avoid losing that mark by getting the sign wrong at the end. So my two routes are yellow and green. You can see my arrows go up and then down, starting here and ending here. And following Hess's law, that's going to be equal to the green arrow, which is going in the opposite direction, but it's the same overall change. What I can then do is start to put the figures in. So I'm going to color code these so you can see where they're coming from. And we can identify enthalpy of formation there, lattice formation. I've got my electron affinity of iodine included. I've got my first ionization energy of cesium included. And I've got my enthalpy of atomization of cesium. So we've got all arrows bar one, and it's this one that we're interested in. So what we can now do is calculate X. We take those figures, and we know that the yellow root equals the green root. So I'm going to put all of those figures in. All I now need to do is rearrange these to make X the subject. So I'm going to take 79 away from both sides. I'm going to take 376 away from both sides. I'm going to add 314 to both sides. And I'm going to add 585 to both sides. I do that, showing the working out here. That's taking us to precisely where I've just described. And we get a value. X is 107. Now it comes out as positive 107, and you don't have to put that sign in, but I always would, because it's making you think about the energetics, about whether things are exo or endothermic. Do bear in mind that if you get the charge wrong and you've done that calculation and it comes out as minus, you get one of the 2 marks. And it's the most common way of losing marks on a question like this, getting the sign wrong. If you find that's something that happens to you a lot, I really do recommend that you try alternative techniques and see if they can get you more consistently to the right answer. Okay, enthalpy of lattice formation for cesium iodide in table 1 is obtained by the experiment. The value obtained by calculating using the perfect ionic model is negative 582 kilojoules per mole. Now here's the value from the table. What do these values indicate about the bonding in cesium iodide? What we're looking at is that these figures are almost identical, negative 582 and negative 585. So we can actually say that this compound is perfect or almost perfectly ionic. What do we mean by that? The perfect ionic model means there is no covalent character. Covalent character would have additional impact on enthalpy changes because you would be overcoming that covalent character as well, the covalent forces of attraction. The fact that they're similar means it's perfectly or almost perfectly ionic. There's no covalent character. Let's move on and let's have a look at table 2, and we're going to show that the reaction provided is not feasible at 298K. Well, the first thing you need to do is calculate delta S. I've got here the sum of the entropy of products, and you can see that because it's half I2 in the equation, I am halving the 117 value. So they are the products, and I take away the sum of the entropy of reactants. That's 130 in this case. It gives me an overall delta S value of 11.3 joules per Kelvin per mole, and we've got the first mark in this question. The second mark in this question is a gift. You've got to really make sure you always put this in. If you're ever talking about feasibility and Gibbs free energy, write the expression delta G is delta H take T delta S. You will almost certainly always get a mark for that. Okay, so now let's put the figures in. Delta G is delta H. We were told delta H is plus 337. We're taking away T delta S. We know that T is 298. So we're multiplying that 298 by delta S. But remember, there is an additional consideration here. We calculated entropy in joules per Kelvin per mole. To substitute it into delta G, we need to convert it into kilojoules per Kelvin per mole. So in this case, we would always divide that value by 1,000. When we do that, we've got a third mark for that working out, and we get our fourth and final mark for getting a value of plus 334 kilojoules per mole. So you have proven that the reaction is not feasible because it's not feasible when delta G is greater than 0. Reactions are feasible when delta G is less than or equal to 0. Okay, let's move on to question 2. EDTA, a useful lab chemical found in a wide variety of commercial products, including detergents. Very soluble in water, often used in the ionic form EDTA 4-, and we can see the diagram of that below. It's a multidentate ligand. What do we mean by the terms multidentate and ligand with reference to this reaction? And that's really, really important, because that means you have to actually consider what we're looking at. It's not generally what do we mean by multidentate, what do we mean by ligand. So multidentate, the EDTA can form 6 coordinate bonds. You could have got the mark for saying many coordinate bonds, but you had to specify it was EDTA that does that. And we're going to see why it can form multiple at the final part of this section of the question. What do we mean by a ligand? Well, again, we know what ligands are generally, hopefully, but it has to be relative to this question. The lone pairs on EDTA 4- can form coordinate bonds with the central copper-2 ion. If you look, you can see that we're dealing with a copper complex based on the information provided in the question. Finally, we need to put a circle around each atom that bonds to the copper-2. What we're looking for here is species that are going to have lone pairs. Now, the two that stand out immediately are probably the Ns, because we know that amines have got lone pairs on there. There are mechanisms that we do with that in the amines topic. But we've also got not COOH, we've got COO-. We've got 4 of them. So each of the O- will have a lone pair on there that can donate to form a coordinate bond. Let's move on to 2b. Copper compounds may be used as fungicides in vineyards. When used in this way, copper-2 ions can enter the water supply, cause problems because they're toxic in high concentrations. The water supply near a vineyard can be tested for copper-2 ions by forming a blue aqueous complex with EDTA 4- ions, and we can find out the concentration using a colorimeter. What practical steps would you follow using colorimetry to determine the concentration of this complex in a sample of water? Well, the first thing that we are going to do is calibrate the colorimeter. You may remember doing this in lessons, you may remember certainly seeing videos of it, but you will calibrate it and you get a mark for saying that. How do we calibrate it? Well, bear in mind, we want to know the concentration of the copper-2 ions. So let's actually make a series of copper solutions of varying concentrations, of known concentrations. And what we can then do is actually put these in the colorimeter, we can test them, and we can find each of their absorbances. And what we then get is this graph that links concentration to absorbance. What you will then do with the sample that you're testing is add an excess of EDTA 4- to the sample. We want it to be a saturated solution. We want all of the copper-2 ions to complex. Once we've done that, we can find its absorbance, and then we can map across on the graph to find the concentration. Now that's a 3-mark question here. That is something that is ripe for a 6-mark question. So do be prepared to talk through the methodology of that practical in some detail. Let's move on to part C. We've got the concentration of copper-2 ions in a sample of water determined by colorimetry, and that's 7.56 by 10 to the minus 5. We checked that by titrating a sample of the water with a solution containing EDTA 4-. The EDTA had a concentration of 1 by 10 to the minus 3. So you are asked to write an equation for the reaction that takes place between the EDTA and the complex. Calculate the volume of EDTA solution needed to react with 25 cm cubed of the water. Remember, the water contains the copper ion impurities. And then justify whether this titration would give an accurate value, and if necessary, suggest a practical step. 5 marks to be had here. First one, the equation. So we know we're starting with CuH2O6 2+ and EDTA 4-. We're going to make a complex, and hopefully the earlier part of this question has reminded you that EDTA forms complexes with a coordination number of 6. It encircles the central metal ion and it will form an octahedral complex. So that EDTA 4- will replace all 6 of the H2Os. The overall charge in the complex is the total charge on ligands plus the total charge on the central metal ion. Now EDTA is 4-, the copper is +2, which means that the overall charge here is -2. We know that copper is +2 because we know that water has 0 charge. Now we also have to factor in that we have lost the water, so we're going to make 6H2O there. And this is a good question that could come up in the context of entropy as well, talking about a large increase in entropy here, so we're going from 2 moles to 7 moles. Okay, let's move on and look at the calculation. If you're ever in doubt about what to do on a calculation, if you've been given a concentration and a volume, work out the number of moles. And we're going to do precisely that with the moles of copper. We have got a concentration of 7.56 by 10 to the minus 5. And we have got a volume of 25 centimeters cubed. So we're going to divide that by 1,000 to convert to decimeters cubed. Okay, from there we calculate the number of moles, which is 1.89 by 10 to the minus 6. What we now need to do is follow that calculation through with the EDTA. EDTA, we want to know the volume, so we need to do number of moles divided by concentration. Now we actually know the number of moles that are reacting here is 1.89 by 10 to the minus 6. And we know that because in the copper EDTA complex, there is a 1-to-1 ratio of copper to EDTA. So 1.89 by 10 to the minus 6. And we've got the concentration. We were provided with that here. It's 1 by 10 to the minus 3. We do that calculation, it comes to 1.89 by 10 to the minus 3 decimeter cubed, which is 1.89 centimeter cubed, and we've got our third mark. So now we've got this final bit. Would that give an accurate value for the concentration of copper 2 ions? The answer is no. The volume is far too small to be accurate. It means that if you made any error, the percentage error on it would be absolutely huge. So with any if you think about any titration, tends to be somewhere in the region of 25 cm cubed added. Sometimes a little more, sometimes a little less. But that would be a good benchmark figure to aim for. So for the final mark, what could you do that would mean we would need a larger volume of EDTA solution? And the simplest way to do that is you could increase the volume required by diluting the EDTA solution. If you diluted it by a factor of 10, you would therefore need 18.9 cm cubed. That would give us far more accurate results. Okay, let's move on to number 3. We've got an aldehyde here reacting with KCN, followed by dilute acid. It's forming a racemic mixture of 2 stereoisomers of CH3, CH2, 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 CHOH, and CN. What is its IUPAC name? Well, we've got 2 functional groups here. We've got the nitrile group and we've got an alcohol group. We're going to have to think carefully about prefixes and suffixes there. We have also got to look at the longest carbon chain, which is 1, 2, 3, 4, 5. Don't forget the carbon in the nitrile. There is a carbon chain of 6. So we know that it's hexane. We know that it's nitrile. So it's hexane nitrile, and we have got to remember to include this magic E here. If we don't put the E in, we lose the mark. That also happens with diols and dioic acids as well. But we've got this OH group. We can't call it ol because we haven't got a space as a suffix for it. So we need to use its prefix. The prefix for an OH group is hydroxy, and it's on the 2nd carbon. So the name is 2-hydroxyhexane nitrile. Okay, what could you do to distinguish between 2 separate samples of stereoisomers of what we've made here, of our nitrile alcohol? Well, when you are distinguishing between optical isomers, you use plain polarized light. And there's a really important word to include in this explanation. The enantiomers will rotate the light in opposite directions. Won't bend them, won't turn them, won't move them. It will rotate the light in opposite directions. More specifically, one will go clockwise and one will rotate anti-clockwise. Okay, why does this reaction produce a racemic mixture? Well, let's take a look at a little bit of background here. If I draw out a general ketone, or aldehyde, whatever it might be, and I have got my CN-. I'm doing this in 2 different colours because these could happen equally likely and alongside each other. It is possible that a CN- could attack the C between the R and the double bond O, but it could also equally attack between the R- and the double bond O. So it could hit either side. It's a planar carbonyl group. That's our first mark. The CN- can attack from either side. Gets you the 2nd mark. The 3rd mark, it's equally likely that either of those could happen. Now that means that it's equally likely that you could make either of the optical isomers, which means we're likely to get a 50-50 mix, which makes it a racemic mixture. Let's move on to part D. We have got an isomer of pentanal reacting with KCN and dilute acid, forming a compound that doesn't show stereoisomerism. What would that be? Well, the key to something like this, we want something to not have a chiral centre, and the easiest way to do that is to go for symmetry. So where could I put my C double bond O that would give me symmetry on a carbon chain of 5? And the correct answer is here. We could start with pentan 3-one. If we did that, and then we added KCN and dilute acid, we would end up with this. And that gets you the 1st mark. I've got an OH group, a CN group, a C2H5 group, and another C2H5 group. So the justification for this, for the second mark, is this compound does not contain a chiral center. It cannot show optical isomerism. Let's move on to number 4, a 6 marker. We're given data about the hydrogenation of a cycloalkene and of benzene. So we've got figures there. You're asked to explain the bonding in and the shape of a benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexa 135 triene and use the data in your answer. Now, 6 markers at A level follow a common format in their mark scheme, and ultimately the decision is, have you given a level 1, a level 2 or a level 3 answer? And this is the criteria we needed for this one. If you got insufficient correct chemistry, you didn't get any marks. But there are 3 stages, and there are generally 3 stages in these 6 markers. If you want to get to level 3, you need to have covered all 3 stages and be virtually complete. So I'll talk more about that as we go through the specific indicative content. For level 2, you need to have 2 of the stages virtually complete or all 3 stages attempted. And to get to level 1, 2 stages need to be attempted or 1 stage needs to be virtually complete. So when it has been decided whether you're level 1, 2 or 3, the decision then for the marker is where within that level you are. And that can be based on the quality of your written communication, the use of key words, the logical structuring of your answer. So stopping and thinking before you write on a 6 mark is a really valuable strategy. Okay. So the 3 stages. Stage 1 is the bonding. So to get this, you would need to get at least 2 of these 3 points discussed. That each carbon forms 3 covalent bonds. That there is therefore a 4th electron that will overlap in each carbon. And that this leads to delocalization or a delocalized ring. So you would need to cover 2 of those 3 for it to be considered virtually complete. If you did that, that would be taking you in to level 1. If you got 1 of those 3, you wouldn't yet be on the marking grid. Stage 2, you need to talk about the shape. So it is a planar shape because there are 3 covalent bonds. It's trigonal planar about each carbon. And that would take us to a bond angle of 120. It would also be important to talk about the fact that the carbon-carbon bonds are equal in length. That's because when you're looking at justifications for the structure of benzene, we know that carbon-carbon double bonds are shorter than carbon-carbon single bonds. The carbon-carbon bond in benzene sits somewhere between those 2 lengths. Now, again, if you got 2 of those 3, that would be that you are considered virtually complete. So if both of these were virtually complete, you're now into level 2. If in both of these you had got 1 of the points, you're now into level 1. The final stage, stage 3, is talking about stability. So you can talk about the fact that this is negative 120. You would expect the value to be negative 360 for cyclohexa triene. But the enthalpy of hydrogenation of benzene is less exothermic to the value of 152 is the second point. And this is because benzene is more stable. So again, a reminder, to be virtually complete in a stage, you need to have 2 of the 3 points covered. So you could actually get to level 3 and 6 marks by picking 6 of these key points. Okay, let's move on to part B. Enthalpy of hydrogenation of cyclohexa 1,3-diene is not exactly double that of cyclohexene. Suggest a value and justify your value. So negative 120, doubling would be negative 240, but we know it's not exactly double that. You'll get a mark if you give any value from negative 121, slightly higher than cyclohexene, and negative 239, slightly lower than what would be exactly double the amount. Why is that the case? Well, the double bonds in cyclohexane are separated by one single bond, and you can see that illustrated here. Now, what that means is we can take our knowledge of benzene, where the fact that there is overlap of electrons, and we can apply it to something that isn't benzene. There will be a level of overlap of p orbitals, and that's going to provide some delocalization, which is going to make this slightly more stable. That takes us to the end of the video walkthrough. Thank you for listening, and goodbye.